Hi everyone, welcome to the Bitcoin Kernel Club. Today is the third session, and today we'll be looking at the Rust bindings, or basically the Rust Bitcoin kernel. So this will be a pretty introductory section. So if you have any doubt, then you can let me. You don't have to wait till end of the session. So yeah, Rust Bitcoin kernel. So before getting into the coding part, in this session we'll just look at what is the Rust bindings and why do we need Rust bindings and why it exists, and also why there is demand to use the to I mean why there is the demand for the Rust Bitcoin kernel. So before moving to Rust Bitcoin kernel, I've already said that there are two kind of memory stack. The first one is the native, or basically the C memory, where the C header API, or basically the C or C++ library exists, and here is all the calculation happens. And then another memory part is actually the Rust Java, or basically the bindings that we are interested in exist. And I've already said you that both of them can't communicate with each other because they have their own memory. And yeah, that's the barrier, or basically issue or problem, you can say. And like apart from Rust, there are different language bindings as well. We have Go, we have Java, we have Python, and also we have the .NET. And all of these language bindings are actually derived, or basically wrapped over the C bindings, or basically the original C++ or C library. Okay, so in this session, we'll just look at the Rust bindings or Rust Bitcoin kernel. So before getting into that, let us look into the architecture of the Rust Bitcoin kernel. So what happens is here is the Bitcoin core, or basically the Bitcoin kernel or libbitcoinkernel C library. Okay. Now this is the header API. The header API is above the kernel, or basically the internal C++ classes. The internal C++ classes does all the calculation. The header file provides, or basically exposes all the classes in a more user friendly, or basically more human friendly way, so that if somebody is not familiar with C or C++, they can use this. They can just see this header file and just create or use this library. You don't have to look into the internal classes. And also internal classes are very much complex, and there are lots of internal you know connected, so it's not good, or it's not feasible to use the internal classes. So that's why we have the C API, and it provides the interface, so you can use that. And yeah, so we have got the C API, or basically we have got the header file. This will expose all the consensus critical, or basically consensus logic of the Bitcoin core. Now with this you can create a wrapper. Wrapper basically means, suppose you have a C code. Okay, now there is a Rust, or basically the different language code. Now that code will communicate with the C code, or basically the Bitcoin kernel C API. And for example, we have Rust. Okay, so what Rust will do, Rust FFI bindings, it will just communicate with the Bitcoin kernel.h, and you don't have to worry about this bindings. Now this Rust Bitcoin kernel, now this will expose using the FFI bindings, the Rust FFI bindings. It will expose all the API that was previously available in the C API. Now the only difference is that we'll have the API in Rust. Okay, we'll have the functions or methods in Rust instead of C. That is cumbersome. That was cumbersome using the C API, and now it's very much easy, or basically it's very much safe to use the Rust Bitcoin kernel. And that's why we have got the Rust Bitcoin kernel, that is the safe wrapper, and this will use the unsafe FFI bindings. And why? Because this FFI bindings, it needs to communicate with the C API, and that's why we have the FFI bindings. And the safe wrapper, it will use this FFI bindings to expose in the Rust way. Okay, that's the main idea. And you can create, or you can experiment, or if you have any project in Rust, if you're familiar with Rust, then you can just use this safe wrapper. This is very much safe. You don't need to think any of this part. You just need to go through all this, Rust Bitcoin kernel docs, and you're good to go. So yeah, there might be a thought that uh, why this one is unsafe. I mean, Rust provides the safe structure, but why this one is the unsafe part? Because I've already said you all the C API or all the C header file, all this uses the pointer approach. So for that reason, because it's a pointer, so for that reason you can't use safe Rust. So you have to use this extern C, and this basically means you have to use the unsafe part. And above that, we'll have a safe wrapper so that everybody can use that. Now this one is safe, and you can use this safe wrapper, and you're good to go with the Rust application. So this was the architecture. And also we can look how F5 works. So before that, I'll just show you the repo for that, for the Rust Bitcoin kernel. So here you can see this is the Rust Bitcoin kernel. Sebastian is actually maintaining this Rust Bitcoin kernel. And if you look here, we have libbitcoinkernel sys module, and this generally contains the original C header API. Okay, if you go into this Bitcoin folder, then this is basically the clone of Bitcoin Core. Okay, because for the C API you will need the whole Bitcoin Core repo. Inside the kernel folder, we'll have this header file. Here you can say there is the header file. So again, getting back to the libbitcoinkernel sys folder, you'll have you see this is actually a crate. Okay, like I already said you about this. We'll have the unsafe FFI bindings. This is actually the unsafe crate, you can say. And we'll use this unsafe crate, or basically FFI crate, and then create a safe Rust Bitcoin kernel crate. Okay, so you can use this, but this one will be unsafe, so it's better to use the safe wrapper. That's the main idea. So if you see here, this is actually a crate, or basically the FFI bindings. Build.rs contains all the you know all the code for bindgen. Bindgen is actually a crate for Rust, which generates the equivalents or FFI bindings. It generates automatically FFI bindings for the C API. Okay, or basically the C code. So here you can see which is defining part to directory and part to build directory, install directory, and then here are some CMake arguments, and then all these function jobs and all these arguments. And yeah, after this, it will create a libbitcoinkernel sys crate, and then that is actually the FFI crate. Using that, there will be a safe wrapper. You can use that, the safe wrapper. So that is pretty safe. So if we go into cargo.toml file, here you can see uh, we're just importing the libbitcoin kernel sys crate. That first this crate will be created or basically built, compiled, and then we'll use this crate to to build this safe wrapper. So that's the main idea. We are actually following the two crate method. The first one is FFI bindings, and the second one is actually the safe wrapper. That's what I've said here. So now, if you look into the how this FFI or foreign function interface works. So what happens is this is the Rust side, or basically this is the safe Rust side, which is exposed to everyone. If they are using the Rust Bitcoin kernel, this is the thing that has been exposed, and none of the other things is being exposed. But you can just use this one, and this is actually safe. Okay, that's why it's better to use this crate, and you can create a context and trade for the context as well. And then when we compile it, it will connect to the FFI bindings, like what I have already said, the Bitcoin kernel SYS, the crate, it will connect to that, and that will actually connect with the C API. Okay, because after all, we want this Rust Bitcoin kernel or the Rust bindings to communicate with the C headers, and the FFI bindings provides the bridge between these two. Okay, so that's the main idea. And as far as I remember, all of the different bindings follows this same structure. Even for Java there is a J extract which follows the same structure. It has a kind of FFI, FFI function or basically code that acts as a bridge between the Java part and the C part. Same goes for Python, I suppose, and same goes for Golang. Uh, uh, we can just go through the docs of the Rust Bitcoin kernel. So you can just you can just search Bitcoin kernel in the doc.rs, and you can find this Bitcoin kernel crate. And so this crates enables Rust application to leverage Bitcoin Core's consensus implementation. It provides safe wrappers around the C API exposed by the Bitcoin kernel. Okay. Key features, if you see, then it currently provides block processing, crypt verification, chain queries, event notification, and memory safety as well. I suppose in the next version we'll also have something block header validation as well, because that PR was merged in the origin, or basically in the C API. Maybe in the next some days we'll see the API for the block headers as well. So if you look into the code of the Rust Bitcoin kernel, then likewise you can just import all the parts of the Rust Bitcoin kernel. You can create a context if you want to do a context validation. If you don't want to do context validation, then you can just use the script verification that doesn't require any context. Context means, uh, like the whole blockchain. So that's the meaning of context. You need whole blockchain to validate uh, blocks or something like that. For the script validation, currently we don't require any context or the whole blockchain state. And then we also have event notifications, chain traversal as well. So chain traversal means, suppose you have a data directory, or basically you have a whole blockchain data in any format. For example, you have in .dat format the whole blockchain state. Now you need to query that the whole blockchain. You want to get the uh, you want to get some transaction, or basically some block. You want to study a block. You don't have, suppose you don't have internet connection and you just want to study a block, but you've got the whole blockchain data. Now you need to query that. So you can use this API to query all the whole chain, or the whole blockchain data that you have. You can query, or basically you can also validate whether this transaction is valid or not with respect to the whole blockchain state data that you had.
You
And
just
yeah.
if even before moving ahead, by the data you mean the IBD? I mean when you're offline.
Yeah. Whole blockchain data, yeah.
Okay. So you're not connected to any other node, but you have your own IBD, so we can use the chain traversal to in order to read the required things, right?
Yeah.
Okay. One more thing, Yuvi. Like you have mentioned that there is an unsafe part, which is the FFI thing. So can you please explain about why it's unsafe? I mean, you have mentioned about the pointers and all of that thing. Can you expand a bit on that?
Yeah, sure. So if we go here, so like I've already said that uh, if you use Rust Bitcoin kernel, then we'll actually have two part of the memory. For example, we'll have a C memory. Now, why do we have the C memory? Because we are actually using the C header API, and C header, or basically the internal structure of Bitcoin Core, uses the C++ classes and structure, something like that. Now that will be stored in a native C memory. Now Rust can't, the safe Rust can't actually communicate with this native C memory. So for that reason, you need to use the unsafe. So this the unsafe, or basically the FFI, bridges between these two part. That's the main idea behind why we need the FFI, or basically unsafe Rust.
Yeah, that's clear, Yuvi. I mean, I'm asking why it's unsafe. I mean, why it's considered as unsafe with respect to the pointers that you have mentioned.
Because if you see in Rust that uh, you know like all the borrow checker and all the traits, there are some features. I'm not familiar with Rust, but there are lots of features like the borrowing part and ownership part. So
Yes.
if we use this FFI part, that doesn't apply, because now we are dealing with pointer. So you can't have ownership for a pointer. So for that reason, whenever we use this extern C, so that means that ownership rule doesn't apply here. So that's why it's considered as unsafe.
Okay, gotcha. Thank you, Yuvi.
Yeah. Yeah. So that's why the FFI bindings provides the unsafe part, but uh, we also have a safe wrapper which provides the safe features of Rust. You'll have all the owned types and borrow types, extension traits, something like that. And also, one more reason why you should be using Rust Bitcoin kernel. If you have a Rust project, then if you want to leverage the Bitcoin kernel project, or basically the consensus engine, then it's better to use Rust, or depends upon your project. If it's in Java, then it's better to use the JDK Bitcoin kernel. And because in the C API, the error handling, it's not actually robust. It's just kind of generic, you know, like for example, if script verification was not succeeded, then it will just print 0 or -1. For example, minus one means it failed the script verification, but zero means it passed the script verification. But there are lots of reason why this script was failed. So for that reason, it's better to use language bindings instead of the C API. Now, for example, this Rust Bitcoin kernel, this provides robust error handling. It provides system errors as well. Okay, whenever there is some error or basically crash in the unsafe part, then it will just give you system errors in a safe way. And then we also have a kernel error, which provides all the different types of enums for the error. And then what else? Yeah, this I've already said that why we should use Rust Bitcoin kernel, because it provides memory safety, no null pointers, no buffer overflows, and that's the main idea. And it is also type safety, compile time checks, strong typing, and also this feels like it is written. It is native Rust builder, and it has robust error handling as well. What else? Uh, yes, some of the use cases or where the Rust Bitcoin kernel has been used in different Bitcoin projects are, we can look at that. The first one is actually a kernel node. So with Rust Bitcoin kernel, you can make your own full node. Full node means that can validate blocks, send transactions, or basically relay transactions, relay blocks to the peers and connect to peers, and also listen to the incoming request and all the blocks and transactions. So here is a basic implementation of the of not a full node, but actually using the Bitcoin kernel of kind of Bitcoin client or minimal Bitcoin client. This is actually very minimal, but this really helps for the testing part. So this is an experimental Bitcoin node written in Rust using the libbitcoin library, and this uses Rust Bitcoin kernel, and this will this doesn't serve any blocks, or it just validate blocks, and yeah, it's just meant to showcase the limited initial API of the kernel library. And also the IBT is currently done from a single pair, which is selected from the DNS seeds, hard-coded DNS seeds. Yeah, this is actually minimal, but yeah, in the future we might have something, a full node written in Rust using the Bitcoin kernel API. Yeah, and the next is Floresta. So if you are familiar with Floresta, is also a lightweight Bitcoin client, uh, which uses UTXO as their protocol. This is something different from Bitcoin Core or Bitcoin Knots or something like that. This is actually a bit different because it uses UTXO as the protocol, and UTXO doesn't store whole UTXO set, but it does store all the blockchain data. So yeah, so Floresta actually uses Rust Bitcoin kernel as their script interpreter, or basically script validation part. They use the Rust Bitcoin kernel. Previously, they had been using libbitcoin consensus, which is actually deprecated, and that is also not that was not a complete library, but Bitcoin kernel provides robust script validation and the block validation as well. So Floresta uses Rust Bitcoin kernel. So what else? What else we can discuss? Uh, we also have a fuzzing for the Rust Bitcoin kernel, and you can fuzz whether there is some difference between what is the expected value and what's the uh, the output. So you can fuzz this Rust Bitcoin kernel, and we have the QA assets here as well. It's given here. Uh, so you can just go through the examples folder, and example, I guess this contains the silent payment scanner. Yeah, silent payment scanner. It uses Rust Bitcoin kernel. This will actually scan all the blocks, and whether that blocks contains silent payment transaction or not. So this will just scan all the blocks. And where does the Rust Bitcoin is used? The Rust Bitcoin is used. Suppose we are scanning a block, and we need to see whether that transaction is silent payment transaction or not. So for that reason, you need to validate that script, and that's where the script validation comes into play. So for that part, we use Rust Bitcoin kernel to scan the script, and I guess for the logging as well. Yeah. So suppose uh, if there was a script validation and we failed the script validation process. Now the C API, it will just provide 0 or -1, but it does provide the logging and the notification. And logging notification contains all the error details, why this script validation was failed, why this block validation has failed. So it contains all the robust reason why this script or block validation failed. So Rust Bitcoin kernel uses that logging and the notification part. It parses that, and it provides in the form of enums value, enums. So whenever we have a script validation failed, now the Rust Bitcoin kernel, it automatically provides like why this has failed. So you can actually also use the logging feature, and but if you don't want to use the logging feature, then the Rust Bitcoin kernel automatically provides the error message or the error reason. And yeah, what else? Um, okay, yeah, we have the block header functions as well. So you can just uh, you can do all the calculation related to block headers, such as what is the uh, block hash, or basically what is the what else? Yeah, previous hash timestamp bits, the version, the nonce as well. Uh, Apart from block header, we yeah, coin as well. Coin, it's actually the UTXO. So in the C API, the coin is actually the UTXO. Yeah, this was it for this session. If you have any doubt, then you can just ask me.
Yes, Yogi. So I have a question with respect to the silent payments. I mean, if you can define what a silent payment is and why do we need to validate it using the Bitcoin kernel?
Okay, I'll just give you a brief idea. Silent payment is actually a new protocol which is not merged, or basically there is a lot of works going on in silent payment. Silent payment what it does is, for every transaction, or basically, for example, you want to receive a Bitcoin, or and you want to send Bitcoin to someone, then for every transaction you need to create a different address for sending the transaction. So that is actually a problem. So you need to uh, change the address every time, and that's actually a problem that silent payment solves. So what silent payment solve does is, actually it provides a static address. So you will have a static address, for example, uvic.sp dot something like that. Then whenever you send the Bitcoin transaction to that static address, now what silent payment protocol does is actually computes a different Bitcoin address every time someone sends a transaction. So for computing the different address from the static address, the computation part is where the Bitcoin kernel comes into play. We need as far as I remember, we need the ECDSA computation, ECDH computation, and for that computation part, we need Bitcoin kernel. I mean, we can leverage Bitcoin kernel. Apart from that, you can definitely use other libraries, but you can use this as Bitcoin kernel. And also, while scanning a block, for example, you are creating a new silent payment wallet, and like someone has sent to your static address, but you haven't seen that, or basically your the wallet hasn't seen. So first it will scan all the blocks, or basically the blockchain, and while scanning it will see whether this static address, whether someone has sent the Bitcoin to the static address or not. For that reason, it needs to scan the whole blockchain. So while scanning, it needs to validate block as well. So for that reason as well, we need the Rust Bitcoin kernel. That's where the silent payment comes in.
Okay, gotcha. So, few questions. I mean, just like, uh, so does silent payment, in a way, is mimicking the exact behavior of a HT wallet? Like a HT wallet simply does generate different transactions, which is similar to what the silent payment wallet is doing. I mean, it is generating the same different addresses based on the static address that it's been set. So, like, what's the difference between is it mimicking, or is it wrapping up the HT wallets, or what it is?
No, I don't think so. It's wrapping up. That is actually a different protocol. There is a lot of computation behind this. Uh, like HD wallets, it generally creates all this, addresses using the parent address or something like that. And but silent payment, it has a different kind of private key and public key. And using the public key, using the private key, it creates a different transaction, or basically different address whenever someone sends you Bitcoin. So you'll just have a static Bitcoin address, and it will, using that private key, it will just create lots of addresses whenever someone sends you the transaction. And using the public key, it will validate whether this transaction belongs to this static address, or basically it belongs to you or not. So there's a lot of difference between HD wallets and silent payment.
Okay, got it. That brings me to another question. Like, this with respect to the thing. I mean, the error handling part that you have mentioned. The C API will throw you -1 or 0 based on the errors that might happen in the C part, which is the unsafe part. So, like, I was slightly excited to know that. I mean, C handles everything in the memory with respect to the pointers. But when a particular error occurs, it uh, in the Rust side, it is showing in the form of the enums. I mean, when it's a enum, when you're declaring a error, then it obviously follows the language of the ownership and all of that thing. So I was quite excited, like how, like, the Rust side is speaking some Japanese, and C is speaking some and Chinese. So there must be some wrapper within that FFI, right, which parses the memory into the memory ownership within the Rust, right? Am I correct?
Yeah, so just a second. Uh, I'll just show you. So yeah, this is actually the header file, and so yeah, if you see here we have a enum. Okay, this is actually enum. This is how we define enums in C, and whenever we yeah script key verify, yeah. So if you see, this is actually the C, or basically the method for for verifying the script, and it returns integer value. Okay. Now, if you see here, will it will also take this value, or basically a pointer to this script verify status. Now, if you look into this script verify status, uh, this is actually a enum. Okay. So what happens is C, for the function, it will return integer value, but it also returns, or it doesn't return, but it takes a pointer to the script verify status. Now, if there is some error while script verification, now it will either throw, either of them will be thrown or not thrown, but will be put inside the pointer, the script verify status pointer. Uh, Here, yeah. So we are just taking a pointer to BTCK script verify status. This is actually a data structure. You can think of it as data structure. Actually, this is a data structure, opaque data structure, and it takes the pointer to the status. Now, if there is a error while script verification, it will just return one if the script was valid for this function, and zero if it failed. But as I said you, it already takes the pointer to this script verify status. Now it will change. For example, if there was a script verification error, this status value, or basically the BTCK script verify status value, will change to something like, something like this invalid error invalid flags combination. Okay, so if you use the the C API, you'll just get 1 and 0. But if you use the Rust Bitcoin kernel, it will show you this. If there was zero, okay, if it returned zero, then it will match. It will use the trait matching, and it will check whether this status returned this. If it returned this, then you will have a string error, like this script contain error in invalid flags, or if it contains this, then error spent outputs required. So yeah, that's how the error handling is handled. I guess that answered your question.
Okay, so the integer value that's being returned, the Rust will somehow resolve that into the error part, right?
Yep. So the FFI, what it does is the FFI will like it will do the matching with this script verify status, whether this script verify status, the pointer, whether it returned okay. If it returned okay, that means the script verification was successful. If it failed, then either of this script either of this error will propagate. or basically it will be stored in the status pointer. So that's why the FFI will actually check or basically match what is the status pointer, what is the value of the status pointer. So if you see here in C API,
Mhm.
so this is actually not an integer. Uh, this is just a name of the of the enum variable or the enum member, but actually what it contains is it contains 0, 1 and 2. That is pretty pretty useful. Like you don't have to compare the string, instead you can compare 0, 1 and 2. So yeah, that's how the Rust FFI handles it. And
Okay. Required UV. And one more thing, like here, as you mentioned, like based on different situations, it might return an int, or it might return an entire enum member from the same. So that's where some sort of conflict might happen, right? Like, is that the thing?
yeah, yeah, that's the main idea. And actually script verification, I mean there are lots. I mean I can't remember, but there are 50 to 60 reason why script verification might fail. But for this I mean the current kernel API, it just exposes only two reasons why it failed, but there are a lot, 50 to 60 reasons. And
So the
I
Rust
can,
part will be handling all of that thing, whatever the errors, the enum based errors things. The Rust part will handle all of that thing, and it will show that this is the exact error which happened in C.
yeah, yeah. So C, you have to do extra work, like you have to compare again with whether there's this was why this failed. You have to match that. But Rust will actually, if it failed, Rust will give you the string return why it failed. So that's the
Okay, got it.
main reason why we should use Rust Bitcoin kernel if you have a Rust project. So if you see here, I've made a script error, expose the script error. There are lots of script error. So I'll just go through the Bitcoin kernel.h. Yeah. So if you see here, there are lots of script error enums values. So yeah, there are lots of. So if there is a
मैं
lot of
आपने फोन
requirement
करना था
for exposing the script error, then we'll definitely expose all the script error. So every script error has a specific integer value. So now you don't have to compare the string, you can just compare with the integer value.
Okay, with that answers my question in detail.
Yeah. Uh, So anybody have any doubt? Something? Okay, so I think this was it for the session.